going to do a chemistry review. I'm going to start with chapter 4. This is going to be chapters 4 through 7. This first video will be chapter 4. So I'm going to go through the chapter review that's from the book on page 124. So, what is the wave-particle duality? The wave-particle duality says that particles of energy, such as light, photons, can be thought of as particles, a stream of particles, but they can also be thought of as waves, as having characteristics of waves. Some people might like to think of little packets of light having waves in them, or you can think of photons moving in a wave-like pattern. Neither of these things are correct. None of these four concepts is correct, but it's our best guess as to what happens in nature. So it's just a model to help us explain what's going on. But the truth is we don't actually know exactly what's going on. So we call it the wave-particle duality. In this chapter, we talked a lot about those waves. So we had different types of interference between waves. So if we had one light wave coming in like this, and then we had another light wave coming in like this, that matched this wave so that their peaks are at the same point and their troughs are at the same point, they're going to interfere with each other and get bigger, greater amplitude. And this is called constructive interference. Now, if the opposite happens, we have one wave like this and another wave like this. Is that right? This one is a trough. There we go. So these waves, this one's up while this one's down. This is going to be destructive interference. And these waves will actually cancel each other out. All right, let's see. We talked about electron orbitals in this chapter. So according to the Aufbau principle, we put electrons into orbitals. The first orbital is sphere-shaped, and it's called an s orbital. There's a 1s orbital. The next orbital is sphere-shaped, and it's 2s. They're called s because they're sphere-shaped. So 2 electrons can go into the first orbital, so we call it 1s2. We fill it, according to the Aufbau principle, we fill that orbital first with electrons. So 1s2, next orbital is 2s2. The next orbitals are 2px, 2py, and 2pz, and each one can take 2 electrons. These are called the p orbitals. Each one can take 2 orbitals. Each orbital can take 2 electrons for a total of 6. And these are dumbbell-shaped orbitals. So when we fill electron orbitals for an atom, we go 1s2, 2s2, 2p6, and then the next one is 3s2. Then we have 3p6. After that is 4s2. And after that, after 4s2, we go to the d orbitals. Okay? The d orbitals are really large. And what is their shape like? So there's a bunch of them, and they're shaped really funny. They can take, there's 5 of them. Let's see, can you see still on the screen? Okay, so the d orbitals are shaped like, one's shaped like a pacifier with a donut around. The other ones are shaped kind of like various iterations of this. So you get the basic idea. There's 5 of them, and they have these different shapes. So they're bigger than the p orbitals. And since there's 5 of them and each one can take 2 electrons, 10 electrons can fit in this 3D orbital. Okay? We'll do an atom in a minute where we fill all of these. But after the 3D, then we get 4p6. Then we go to 5s2, 4d10, 5p6. Okay, so whenever we get to the d orbitals, they're 1 energy level behind. Okay, so I want you to know the shapes. The spherical shape is S, the dumbbell shape is P, and this crazy shape is D. All right? So let's do an atom. So I'm going really fast again because this is just a review. We covered all this in class already. But if we do an atom, we look at the periodic table to help us. So let's do a big one. Let's do SN, tin. It's number 50. So we're gonna start filling orbitals from here. So we'll do H and HE. These are 1s2, then 2p2, sorry, let me start over. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, we to 10 yet? Nope. 5s2, 4d10, 5p2, because we've only got 2 there. Okay, I'll write that on the board. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then we had 5p2. Okay, this is a lot to write, so we can use an abbreviation. Can you see it in there? So we go to the nearest noble gas before 10. So all of these, no matter what atom you're doing, are going to be the same up until you get to that certain one. So we can just use this noble gas, up, closer. We can use this noble gas, krypton, and use that as an abbreviation. And by the way, these ones in group 8A here are the noble gases, and they're called that because they do not react with other elements under normal conditions. Okay, so we're going to use krypton. So all of this, all the way up to 4p6. This is krypton right here, if we were to fill krypton shells. So we're just going to put it in a little bracket and use this as an abbreviation. Then we can just use the rest here. 5s2, 4d10, 5p2. Now, how do we tell what's in the valence shell of this atom? We look at the highest energy level, 5. We've got 2 and 2. So there are 4 valence electrons for tin. Okay? It is a transition metal, so its chemistry will be slightly different. But for the purposes of where we are right now, we'll say it has 4 valence electrons. Okay. So this is called the ground state electron configuration. Now, let's do iodine. So iodine is number 53. So I'm going to use that same abbreviation. I'm going to abbreviate with krypton, since krypton is the noble gas that comes before iodine. And then we're going to start with 5s2. So 5s2, 4d10, 5p, and how many do I have? So iodine is one of the halides in group 7A. So I've got 5p, 1, 2, 3, 4, 5. 5p5. So how many valence electrons does iodine have? In the 5th energy level, I've got 2 plus 5, 7 valence electrons. So now I can make the Lewis dot structure for iodine. So I'm just going to put the valence electrons in this Lewis diagram. We'll go 1, 2, 3, 4, 5, 6, 7. Okay, so now you can clearly see the 7 valence electrons in iodine. Now what does iodine do when it's in an ionic compound? If I had a compound like sodium iodine, sodium iodide, when this gets into solution, it separates into its ions, right? We get a cation. The sodium gives its electron to iodine, making it an anion. So if we were to write iodine's Lewis structure, iodide's Lewis structure as an ion, I'd put another electron there. It's gained this electron from the sodium, right? Because it's an ionic compound. It's gained this electron from the sodium, giving it a negative charge. So this is iodide's Lewis structure as an ionic compound, in an ionic compound. Okay? So, ionic bonds are those in which the electron goes completely over to the other element. Now what happens when you have a molecule like this, methane? These electrons do not go completely over to one or the other. They are shared. Each bond here represents a shared pair of electrons. Now, are these shared equally? No, they are not. Carbon is much bigger and has a much bigger nucleus than hydrogen, so it pulls with the electromagnetic force. Those positive protons pull on the electrons more strongly than the nucleus of hydrogen. So the electrons are going to spend more time closer to the carbon. So these are polar covalent bonds. Okay? So any bond that has a shared pair of electrons is a covalent bond. Covalent means sharing, covalence. When they're shared unequally, it's a polar covalent bond. The only molecules that have nonpolar covalent bonds or purely covalent bonds, purely covalent, are those called homonuclear diatomic. Homo means same nucleus, so they're the same element. Diatomic, 2 atoms. These are the only ones that have purely covalent bonds. So, N2, nitrogen gas, is a homonuclear diatomic. This is a purely covalent bond. It just happens to be a triple bond. Oxygen, O2, purely covalent bonds. The electrons are shared completely equally between those two. Chlorine, F2, again, a purely covalent bond. And then the rest of the halides, chlorine, bromine, iodine. Okay? But in all other covalent bonds, they are polar covalent bonds. So methane has 4 polar covalent bonds, but it's actually a nonpolar molecule because those 4 cancel each other out. Since they all pull in opposite directions from each other, they cancel each other out. So this ends up being a nonpolar molecule with 4 polar covalent bonds. Okay? Now, we talked about metals versus nonmetals. I think that's pretty straightforward. Metals are shiny, nonmetals are not. Metals conduct electricity, nonmetals do not. Metals are malleable, nonmetals are brittle. That's kind of from elementary science. Now, how do we tell the chemical formula for compounds given a name? So if we have calcium fluoride, and your question is, what is the chemical formula? What is the molecular, what's it called? The molecular formula for calcium fluoride. Well, you look at calcium on the periodic table. Calcium is in group 2A on the periodic table, which means it gives up 2 electrons, giving it a 2+ charge. Fluoride is in group 7A, which means it gains 1 electron, giving it a -1 charge. So let's put these together into a molecule. This 1 is going to come over here, and this 2 is going to come over here. That's just a shortcut. So your compound is going to be CaF2. Okay, I'm not going to go through all the Y's right now because this is just a quick review. What about iron 3 oxide? Well, this 3 tells us that iron is going to give up 3 electrons. Oxygen is in group 6A on the periodic table, which means that it's going to take on 2 electrons in order to get to its valence shell being at 8. So it's going to get a 2- charge. So now we can just switch these, and we'll get Fe2O3, which I believe is rust. All right. So one thing we forgot to talk about is electrolytes. We were talking about ionic compounds. When an ionic compound is in water, like we said, it's going to split apart into its ions. Sodium is going to completely give its electron to chlorine. Positive charge, negative charge. In water, or in aqueous environment, these ions are going to be able to carry a charge. So this will conduct electricity. Sodium chloride or any other salt or ionic compound dissolved in water will conduct electricity, and these are called electrolytes. Alright, I believe that is it for module 4. I mean chapter 4. We talked about soap, but I think it might have been in chapter 5. You can turn it off.